Hi, my name is Irzwan Affendy and I did my FYP project on structural and defect changes in charcoal irradiated with gamma ray. This project was supervised by Dr. Siti Fairuz. Carbon is found in abundance in the nature, and two of the most common forms of carbon are graphite and diamonds, which are made of mainly sp2 or sp3 bonding respectively. Now, charcoal, which is made from the carbonization of wood through the pyrolysis process, is a type of amorphous carbon, which means that it does not have a crystalline structure like diamonds or graphite do, but instead they are composed of a mixture of sp2 and sp3 bonding, and the properties of amorphous carbon depends on the ratio of graphitic sp2 and diamond-like sp3 hybridized bonds that are present in the materials. Recent researches on graphite has found that the carbon network can be used as dosimeter for medical application. Given that charcoal are relatively cheap and easy to be manufactured, it would certainly be beneficial if we are able to use it as a dosimetric material. In this project, we will use the same approach that was used to study graphite to explore the potential of charcoal to be used as a dosimeter. In this project, the three types of charcoal made from mangrove, coconut, and sawdust were used as samples. Now, before we proceed, it is important to note that for a material to be considered as a dosimeter, it must have at least these two basic properties. The first one being that the effective atomic number of the material needs to be equivalent or near to that of a human soft tissue, which is around 7.4. So, to investigate this, we are going to do elemental analysis on our samples to calculate the effective atomic number. The second one, the dosimetric material must have a linear dose response. This is to allow accurate measurements of radiation dose delivered. And the dose response of our samples were characterized using Raman, PL, and XRD spectroscopy. Elemental analysis for the three samples were done using energy dispersive X-ray to map the elements that are present in the samples. The figure on the right here that you can see is a typical result that you would obtain from an EDX analysis. This one in particular is obtained for our mangrove sample. Now, using the data, we can calculate ZEF using the Magnot's formula, where A is fractional weight and Z is the atomic number of the respective elements that are present in the sample. The ZEF for mangrove was calculated to be at 6.74, which is quite close to soft human tissue, considering some of the dosimeter that we use today around, they are approximately around 6 to 6.5. Next, Raman analysis was performed on a control samples that was not irradiated and samples that were irradiated with gamma ray at dose range of 2 to 10 gray. The figure on the right hand side that you can see is the Raman spectra of mangrove charcoal. And as you can see, the two most prominent peaks of charcoal are the defect band D and the G graphite band. The G band can be attributed to the in-plane vibration of sp2 carbon atoms, and it is common in all graphitic materials. On the other hand, the D band is attributed to the out-of-plane vibration, and it is only present in a defected material. Thus, the D mode is associated with the presence of structural defects for the material. The integrated intensity ratio ID over IG can be used to characterize defects in graphitic materials. However, when we plot the intensity ratio as the function of dose, we can observe a wave-like pattern here showing a non-linear dose response. Then, similarly, we carry out the PL analysis for our samples. The first and the second peak corresponds to the absorbance and the emission wavelength respectively. Now, by using the emission wavelength, we can calculate the band gap energy for our samples. Looking at the tabulated results below, we can see that the energy band gap also did not show a linear dose response. Finally, we perform XRD analysis on our samples. On the right hand side here, you can see is the XRD spectra of our mangrove samples, and every intense peak that you can see corresponds to the lattice planes that are present in our material. Now, using the Bragg's angle and the full width half maximum that can be obtained from the spectra, the d-spacing and the crystallite size can be calculated using Bragg's law and Shearer's equation respectively. And just like before, the changes of these parameters as function of dose were observed to again characterize the dose response. To conclude our project, our charcoal samples showed effective atomic number within the accepted range. Unfortunately, as you can see from our Raman PL and XRD analysis earlier, the structural defects did not show a linear dose response. So this may be explained by the unique ability that graphitic materials possess, which is the self-repair mechanism upon irradiation. So when these samples are irradiated, there are two processes, which one is radiation-induced defects and one is self-repairing mechanism. And these two processes are actually competing over one over another. And as you can see, when the structural order of the sample is relatively increasing, this means that the self-repairing mechanism is dominant over the defects generation effects. So this concludes my final year project. Thank you.